By the time I'm done, you should be able to solve any conservation momentum problem. We're going to look at harder ones after today, but this is the first thing I want to do, and this is not so important that you write this down, but just a notion that you put in your head, is why is momentum conserved? So the universe is a very complicated thing, but let's look at a universe that has two objects, okay? Object one is spaceman A, and object two is spaceman B, okay? And this I know is true, and that is that if A is going to change their momentum, it's because B pushed on them, and that's because there's no other thing, right? And we can't change our own momentum by pushing on our body, right? It's like, it doesn't really work, right? Yeah? Kind of a thing. My parents used to joke with me, like when I was a kid, like the car would slow down going up the hill, and they would say, push on the back seat, you know? Like we'd be all in the back seat, and they'd say, push on the car to make it go faster. Does that work? No, I knew in my heart of hearts too that would not work to make the car go faster, right? But they would always say that. Did your parents do that to you? No, not so much. I don't know, but that was we also would anyway. We won't go there. Okay, but anyway, if B is going to change their momentum, the only way that they can change their momentum is that A pushes on them, right? And these are impulses. The second thing I know that's true is that in this universe anyway, that the force on B is opposite the force on A. Yeah? Right? And so that if B pushes A that way, A pushes B this way. These are equal and opposite forces. This is Newton's third law, right? And then of course the final thing, and I know this is true, is that these equal and opposite forces exist for the same amount of time. Now you can try to do this. You can try to like touch something for a different amount of time than it touches you, but it's very difficult, right? It's like it's always the same amount of time, right? Isn't it? Yeah. It's like anyway, you know. Okay. So here's where we're headed, right? Is that if changes in momentum come from forces, if the forces are equal and opposite, if they exist for the same amount of time, then don't equal and opposite forces acting for the same amount of time lead to equal and opposite changes in momentum? This is crazy. So that means that the net momentum, the total momentum before and after has to be the same. The net change is zero, right? The total momentum before and after is what it's the same, right? So if we have a couple air track gliders like this, and they collide, move these out of the way, right? If these guys collide, right? Before that collision, there was the same exact total momentum as after the collision, yeah? And it doesn't matter what they're doing, they could be hitting head on, right? Like that. They could be going like this, like that. The total momentum, if we add up all the momentum of the whole thing before and after the collision, it's always the same, right? So that's where we're headed. But first, so let's solve a problem here. Okay, 60 kilogram Sally, and that's her name. She wears name tags. It says on there, 60 kilogram Sally. Really, that's who I am, right? Going 4.5 meters per second, collides head on with 80 kilogram Bob, and that's his name too, right? On his thing it says 80 kilogram Bob on his, right? He's going 2.3 meters per second. But what you need to understand is that there's a little more to this than just these names and their velocities, okay? Sally and Bob were, they actually dated quite seriously in college. People all thought they were going to get married, right? And everybody was assuming they get married, right? But Bob got a good job in, in private industry. Sally was, with her language skills, got a job with the American Embassy in Paris, right? And so are we picturing this? She goes off to Paris, he's in the United States, right? They stay in touch. I mean, they're still dating, they're still in love, right? But they're both in these really intensive careers, and pretty soon they just sort of stop sending, it just kind of slowly peters out, right? And this is sort of a sad thing, right? And it's not like they find anyone else in their life and they start dating other people. It's just like there's this thing that was in their life and now it's not there anymore. Jen's heard this whole story. Have you? No. No? Okay. I thought you were in there for the other class. But anyway, yeah, it's always the same story, right? Now, it's been like 5 years since college. Bob finds himself in Paris on a business trip, right? Now, here's how bad it's gotten. He hasn't even told her that he's going to be in Paris. He's so busy, and it's like at some point he realizes he should like drop her a line. You know, it's like, I'm going to be in Paris, right? But at some point, if you like tell somebody like a week before you're there, that's kind of insulting, isn't it? Right? Like this person that was so important. So he goes to Paris. He doesn't even tell her, right? Are you picturing this? And it's very cold. It's springtime in Paris, but it's very cold. It's a very cold spring, right? And the Seine River, which flows through Paris, is like frozen, smooth. In fact, you'd almost say the surface of the Seine is frictionless. Yeah? Yeah, essentially frictionless, right? And they see each other on opposite sides of the Seine River, right? And picture there's like petals of blooming trees floating down, and there's Enya playing. Are you picturing this? Enya, yeah, right? You know? And the music starts to swell. Their eyes meet on the foreign city street, right? And they run toward each other with well-known masses and velocities. Yes? And they collide on the surface of this frictionless, yeah? Right? Okay. Now there's all kinds of questions we could answer here. One question that we could answer is, we could try to answer, right, is a relationship at this point a realistic thing? If they couldn't be bothered to maintain the relationship they had, is it realistic that they're going to now start, right? Have they changed, right? Have they changed so that they're no longer really all that compatible? Were they compatible to begin with? Have they placed each other on this sort of ideal pedestal of like this thing, right? Okay, there's all these questions, but the main question we're going to answer is, she's taller, that's okay, if the girl's taller, okay. The main question we're going to answer, though, is what is the velocity, the post-collision velocity of their embracing bodies? Yes? Okay, that is the question that we can answer, and pretty much nothing else, right? Okay, so the thing to do is to draw a picture, right? So you've got Bob and Sally, okay, and they are running, here we go, right? Okay, and I like to put this is 80 kilogram Bob. 60 kilogram Sally. She's going 4.5. And he's going 2.3. Does she want the relationship more? Right? You know? Yeah, right. Okay, and here they are. It's like, there we have it. Okay. It is a heart. It's a lopsided heart.
It's like a real heart.
There.
Hearts are so hard.
All right. That's a heart. That's definitely a heart. Okay, now, here's what we have to do. And this is key. This is like the key thing. If you come away with nothing else today, this is the key thing. I'm going to make to the right positive. That makes this velocity positive, but this one negative. Okay? Now, that's the only key. Right? That is the trickiest thing. And pretty much, why is hers negative? Because she's running to the left and he's running to the right. So to the left is negative, to the right is positive, right? Now, if we miss that minus sign, this means that they're running toward each other, right? If we miss that minus sign, doesn't the film change genres? Yeah, like she runs away, right? She sees him and just starts, luckily she's running faster than him, right? No. Okay, so we've got to have the minus sign in there, right? That's very, very important. And now all we have to do is just add up all the momenta here and set it equal to all the momenta there. And this is really easy. I just do like this. I go 80 kilograms times 2.3 meters per second, right? Plus 60 times, right? Equals, and then I'm just going to go, what's 60 plus 80? 140, right? So you see those people in the halls sometimes, right? And you just say, yeah, we could add your masses together, right? You know, or Zitz. You guys read the cartoon Zitz? Yeah, Rich and Amy.